Hello everyone and welcome back. Today I'm going to show you how to recognize an angular collision problem and how to properly set one up. You may remember collisions from linear momentum, and the truth is this isn't really that much different. In fact, we're going to do a derivation, and how this derivation happens should be really familiar. Let's start with this. So what I have on the screen right now is for linear collisions. One of the biggest rules of momentum is, as long as there are no outside forces involved, momentum is conserved. So initial momentum equals final momentum. We are going to have two objects in play. So momentum A initial plus momentum B initial equals momentum A final plus momentum B final. I break that down again, and you have mass times velocity initial for each object and mass times velocity final for each object. So this boils down to total initial momentum and total final momentum. And at that point, you're just looking for the missing variable. So if linear momentum is conserved, then so is rotational momentum. Therefore, initial rotational momentum equals final rotational momentum. Rotational momentum object A initial plus rotational momentum object B initial equals rotational momentum object A final plus rotational object B final. Therefore, instead of mass, we use moment of inertia, and instead of linear velocity, we use angular velocity. So rotational momentum object A and rotational momentum object B initial equals rotational momentum object A and rotational momentum object B final. And here we have our rotational momentum collision equation. Fundamentally, it is the exact same concept, even with directions. For velocities, right is positive, left is negative. For angular velocity, typically counterclockwise is positive and clockwise is negative because of the unit circle, although I'm going to show you why that rarely comes into play, as it's usually easier just to set whatever the current direction of velocity is as positive. So I'm going to take this, and I'm going to put our rotational momentum equations at the bottom, and let me show you what a sample problem looks like. Okay, for this problem, we are going to use this device again. It is very simple. It's just a disc with an axle here, and you take the disc and you spin it around. So let me show you a common rotational collision problem. A 3 kilogram, 20 centimeter radius disc is rotating with an angular speed of 5 rotations per second. So this disc is spinning around. While this is happening, you drop a 0.4 kilogram piece of clay onto the disc. The clay lands 18 centimeters from the axle and sticks to the disc. What is the final angular speed of the disc? So one of the reasons why I wanted to introduce this is because sometimes new students have trouble recognizing this as a collision type problem, because unlike linear, they're not running directly into each other. This disc is spinning around and you're dropping a piece of clay down onto it. So the clay sticks to the disc and then starts revolving around with the disc. Okay, let's analyze this a bit and start how we usually start, which is by listing givens. Mass of the disc is 3 kilograms. Radius of the disc is 20 centimeters. I'm just going to put that right to meters. Something I'll notice right here is we can immediately go directly to moment of inertia. I'll come back to that. The initial angular velocity of the disc is 5 rotations per second. The mass of the clay is 0.4 kilograms. The radius of the clay is 0.18 meters in the center axis. Since it is rotating around, the clay is also going to have a moment of inertia. As a quick reminder, the moments of inertia that you should actually have memorized are these 4: point mass, ring, disk, and sphere. So the disk is 1/2 mr squared, 1/2 3 kilograms times 0.2 meters squared gives me 0.06 kg meters squared. Now the clay doesn't really have a defined shape. You have a lump of clay, you drop it and it hits the disk, then starts twirling around the center axis. Well, if the entire piece of clay starts going around the center axis, that means the clay acts as a point mass, which is simply mr squared. 0.4 kilograms times 0.18 meters squared gives me 0.013 kilograms meters squared. All right, I'm going to make this smaller so there's some space to work in. Let's lay out our new equation. I have the initial moment inertia of the disc, initial angular speed of the disc, plus moment inertia of the clay, initial angular speed of the clay. Now, just like linear, the equal sign represents the collision. Everything to the left of the equal sign is before the collision. Everything to the right of the equal sign is after the collision. And after the collision, they are stuck together. The clay lands on the disc and then spins around with the disc. Therefore, if they are stuck together and spinning at the same rate, they will have the same final angular speed. Another way to put it is this is an inelastic collision. And when it comes to rotational physics, inelastic collisions are easily the most common type that you will be dealing with because they are very easy to set up. The AP exam loves these. And there are a few different ways to set them up, which I'll talk about in a minute. So if they're stuck together now, they have a combined moment of inertia. Just like if this was linear, they would have a combined mass. For final angular speed, I'm just going to put omega f because, again, they have the same final angular speed. Something else we can notice at this point is that before the collision, the clay is coming straight down, and you're not dealing with anything on that axis. The only thing you're dealing with is rotational. And before the collision, the clay has no rotational velocity. Therefore, this right here is 0. So I can just get rid of this entire section right now. Something else we should notice is setting up our red flag. If these two objects are sticking together and moment of inertia is increasing and momentum is conserved, that means the final angular velocity should decrease. So we should get less than 5 rotations per second. Let's find out. Omega final equals moment inertia of the disk plus angular speed of the disk initial plus the combined moments of inertia, 0.06 kg meter squared, 5 rotations per second. Notice I did not convert it. I'll tell you why in a second. Over the combined moments of inertia. Now what's about to happen here is all these units are going to cancel, which means your angular speed can be rotations per second or radians per second or whatever you want. I'm just going to leave it. The one thing we do know is our final should be smaller than this. And we can already tell that is going to happen because my denominator is larger than my numerator. When we do the calculation, we get 4.11 rotations per second. And that is our answer. So if you did this problem with me, you should be able to recognize an inelastic rotational collision pretty easily now. What I will tell you, however, is that anything could have been dropped onto this disk. I could have dropped another disk. I could have dropped a ring onto this disk. And that would mean that the moment of inertia equation for the second object would have been different. If I dropped another disk, it would have been 1/2 mr squared. However, if I dropped a ring, it would have been the same because a ring and a point mass have the same moment of inertia equation. I've never seen them do this, but they could have a rotating sphere and then chuck the clay onto the sphere. If that was the case, the moment of inertia equation for the initial object would have been the equation for a sphere. The only thing I'm saying is 95% of these problems are one object being stuck to the other. As long as you recognize what the moment of inertia equations are and recognize that it's a collision, all you have to do is set up the system and you pretty much can't miss. All right, let's end this video with one simple thing. This is the rotational collision equation because rotational momentum is conserved. Let's take that and add that to our list. So here's our updated linear to rotational list. Again, you should definitely have this written down in your notebook because it'll be very useful. In my next video, I plan to do a higher level collision problem, so be sure to check that out. Other than that, have a good day. This is Mr. M, signing off.